Yeah, so as we said, this algorithm we are going to cover today is probabilistic. I would say one of the powerful classification algorithm. And as we said, go all the way to Markov models, hidden Markov model, etc., or Markov chain process, which is part of AI even. So this is a very popular topic. I would say very common algorithm. Or again, I'll use the term powerful classification algorithm. Yeah. So again, we start with the naive first. As I mentioned earlier, the whole concept of naive is about independency. We will see the objective. So independency. So in naive, because it assumes independency between the features, in this case, the attributes. So this means that it just not only it assign a label or in this one, I would say in general probabilistic method, we don't the algorithm doesn't only assign labels, but also it does what calculate the probability of an instance belonging to again each class, and then select the class with the excuse me with the highest probability. So that's the whole concept of naive. But I said one of the major reason or the difference between the two algorithm we are going to cover here is the independency between the features. So Bayesian network dependency, etc. And here also we mentioned that's why it's very simple, often perform surprisingly well, specialized with again high dimensional again data. So we all know what Bayes refers to. I think we cover that in statistics a lot when we talk about conditional probabilities. So Bayes normally refer to the Bayes Theorem, which is again the mathematical, I would say the mathematical backbone of the algorithm here. And that's what we have here. So probability of an event A given event B, which is probability of A given B, will be probability of B given A times probability of A over probability of B. Now, when it comes to machine learning, I normally will say that, which I think some textbook also say that, probability of B given A is like the training data, because here we are saying that we know the class, which is B, given the features. Maybe it can be more than one, it can be more than one. So this kind of like the training data. Then the whole of probability of A, and also, again, we will go more detail. So let's first of all try to understand the terms here. So we say probability of A given B will be the posterior probability. This is what we are looking for. This is what we are looking for. Then probability of B given A. So that's a good term to use, the likelihood. Then we have the probability, which is the probability of A. And also we have the probability of B, which will be again, the evidence. Yeah. So the concept of, again, as we said earlier, naives, I would say that naives, again, the term naives means, I would say it describes the algorithm simplifying assumption, the assumption. As we said, it assumes that, again, all features that are used for classifications are, again, independent of each other, given the class. For example, let's say if we are trying to classify an email, let's say we're trying to classify an email as a spam, let's say as a spam or not a spam, and we are using words maybe more than one. Let's say example, we are using the word free and also the word money as features. So free and money as features. Now, naive Bayes who are assuming that the presence of free is independent of the presence of, again, money or any other features. So when we already know the email is a spam or not a spam. So in reality, this assumption, I would say it's a false. It's often false. And we will talk about this. For example, if we are classifying something and one of the features is zero, since we are using multiplication or dot product, that means the whole section there will be zero. But that's not the case. That's not the case. Let's say, for example, we say the probability money is 0, probability of money that is spam is 0, and probability of what word I used before, free, it's not 0. But when we're doing the product of them, because we have to do the product of all the features, then take the higher, we will come off. Again, we'll talk about this in the future slides coming soon. So again, so that's the whole idea. Yeah, so this is the main goal here. Bayes theorem for classification. We can see we have the probability of C, K. So that will be our class, given the features. So the features here will be x1 to xn, depends number of features we have. It's equal to the probability of all the features from s1 to sn given the ck, the class, times probability of ck over probability of p, all the features, S1 again to Sn. So as we mentioned earlier, we want to maximize our result, the posterior probability, which is probability of CK giving S1 to Sn. So our goal always is to choose the class CK that maximize. And again, we have example, we see examples. Also, the denominator here, we say it's constant for all classes. So we can ignore it for classification decision because we are using the same features. So let's say we have class 1 and class 2. We want to classify whether based on the features it belong to class 1 based on, but again, in this case, the features, again, they are the same. So wait for a few seconds if it's okay. As we said earlier again, the probability of CK giving S1 to Sn. Also, from the previous slide, this time it will be the posterior probability. Then probability of S1 to, let's say, Sn giving CK, again, will be the likelihood as we have it before, probability of A giving B. Then, of course, probability of CK will be the probability in this case. And the last one, the probability of S1 to Sn at the denominator, again, will be the evidence. That's the probability of observing this, and that's the particular combination of the features, I would say. So anytime we are classifying a new instance, we have to calculate the probability of CK giving S1 to the Sn for each possible class CK. Again, CK can be a number of class C1, C2, etc. And then we choose the class that yields the highest, as we said earlier, the highest posterior probability. So let's wait a few seconds. If no question, let's keep going. I would say that's all the mathematics. That's all the mathematics we have here. Again, everything's based on, again, probability. I would say conditional probability concept. So here again, I would say that when we have the naive part of the Bayes comes in, the naive assumption features comes in. So calculating, let's say, probability of x1 to xn, giving ck directly will be computationally, I would say computationally very expensive, especially if we have many features. If we have many, we can see the product S1 giving CK, S2 giving CK, all the way to, again, SN giving CK. Again, it's product. Yeah, so it will be computationally expensive. Yeah, again, if we have so many features, because again, it requires knowing what the joint probability distribution. We have to know the joint probability distribution of all the features, within each class. So this will require, especially again, if we have a lot of features, it will require a lot of calculations, estimation here, have to be accurate also. So normally to simplify this, naive Bayes make, I would say make a strong, so often unrealistic assumption. So here you can assume that each feature, let's say xi, which is s1, s2, each features is conditionally independent of every other features, given the class again, CK. Yeah. So I'll say, or let's say in the plain terms, we gave the previous example. Let's say if you know the class of an instance, let's say the sperm or not a sperm, then the value of one feature, let's say example contains free or any word, let's say GPA, does not influence the value of another feature, as we said earlier. Let's say another feature is money, free money GPA. They are treated separately, unrelated pieces of evidence, given that, again, we already know it's spam. Yeah. So that's mathematically, this will be, again, the formula here again. Probability of S1 up to Sn given CK again, approximately each one, S1, it fed, S2 have it fed all the way to the end. So I would say that in short, this simplification also makes naive Bayes computationally now computationally feasible and also efficient. Why the independence assumption is, I would say, it's really perfectly true in a real world. In a real world, yeah. Features often have dependency in the real world most of the time. Yeah. So that's the beginning of the whole idea here. And then this is a concept combining Bayes theorem with independence assumption. So this is what, again, as we said earlier, we are looking for. The goal, again, is the mass. We're going to choose the mass. Again, hopefully we understand the symbol, product symbol or something. So here we say probability of CK given S1 to Sn will be probability of CK product of S, so it can be S1, S2, or from 1 to N. Like previous slide, but this time we write it more shorter. Yeah. So let's wait for a few seconds if any question. As we said earlier, the class so what we have here means the class that give us or yield the highest value will be the predicted class for that instance. So this is what the argmass function signified or represent. It retained the argument, in this case, the class CK that maximize the expression. Yeah. Maybe that's all we can say here. Let's see if somebody can put some input. So this is all the mathematics. You can just see that the whole idea here, again, as we said earlier, is conditional probability concept. So here they say how to estimate the probability. And this one I will go through the slide step by step because the steps is right there. So first, of course, we need I would say we need a CK, a probability of, again, it can be CK represent the class. So to find it, it's straightforward. How many instances we have that have CK? Then we divide by the whole training. So let's say we are trying to classify, we have some training data and we have spam or no spam. We have to, let's make it only 10. Maybe easier to calculate. So we have 10 total records or instances. And 8 belongs to spam and 2 belongs to no spam. So what's the probability of spam? Well, it will be 8 over 10. What's the probability of no spam? Then it will be 2 over 10. Yeah. Kind of, that's what we are trying to say here. So the total number of training instances is what we're going to, probability of CK again, equal to the total number of training instances divided by the number of, sorry, I'm naming it, the number of instances in this class CK divided by the total number of training instances. Yeah. So it's like finding the fraction of the part of it, or I would say the portion of it, or fraction. Then secondly, we're going to look for the conditional probability of the features. What's the probability of each one, S1, S2, etc., of each feature, or let's say here probability of SI given CK. So this will be the frequency of the features value SI occurring within the instances of class CK. So yeah, the formula also is given down, which will be again the number of instances in CK where the features SI has a, let's say, value VIG divided by, again, the number of instances in class CK. Plus, the next section, they say if it's a continuous features, then we often assume a specific distribution. It can be Gaussian, naive, I think that's normality distribution. Gaussian naive is assume a normal distribution, normality. And also, in this case, we estimate its parameters, for example, the mean variance for each class, etc. And then that will take us deep into statistics. So let's wait for a few seconds if any question. Now, I will say one thing, the beauty of a naive Bayes here is that I will say that all probability required for the formula can be easily estimated directly from the training data set using the frequency counts. And we will see examples soon. So that's why, again, it's considered, sometimes they call it the generative model, a generative model. It models the distribution of data within each class, And we'll see the example soon. So hopefully we don't have no question on the probability. Example, as I mentioned, let's say we have 100 data, 20 is spam, 80 is not spam. Then probability of spam, which is probability of CK, the class is spam, will be 20 over 100. That's it. Okay, so let's see. I think we have an example. Okay, so this is the example we try, but this is a different example now. So this example said we are doing naive-based estimation. Simple example. The scenario here is to classify if an email is spam or not a spam based on the following words. So here we have Viagra offer free. That's a spam. Meeting date. That's not a spam. Free money offer, spam. Then not spam, hello meeting. So here, what we are going to do, first we can say again, as I said, we said earlier, that's why this model is called generative model. Based on the training data. So again, the previous slide, this means it's a training data because we know the feature and the classes are to whether spam or not spam. So based on the training data, we can just generate the model so easy, finding the probability concept, again, using Bayes ideas and theory on this. So the first, of course, we are going to find the probability of spam. Well, the total was 4, we get 2. Probability of not spam to the same thing based on the training data, 2 by 4. Then next we calculate the likelihood example. So what's the probability of free given the spam? So it will be, we have to count the free. So we have to count so these are the words which will determine spam or not spam. So we have to count the word free in the spam email divided by the whole total spam emails. Yeah. So count free in spam emails divided by total spam email. Then what about Viagra given if it's a spam? The same thing. Count Viagra and spam email. Then what about free given that it's not a spam? Then count free that is not a spam email over total not spam email. And this list will keep going on and on. Then we apply, this is the applied formula here now, probability of spam So here we have two features: probability of sperm given free and Viagra. Then probability of non-sperm given free and Viagra. And it's a product. So let's wait for a few seconds if it's okay. Okay, so let's keep going. Now, this is where we have a problem now. Let's read this section. This is zero frequency problem. We are saying that if a feature value never appears with a particular class in the training data, then we'll say it's zero then. But when we do the product, let's go back here. Let's say free doesn't appear, but we have Viagra, we get something. Or the sperm also, we get something. But if one of the probability is zero, then the whole thing again will be zero. So this is one of the major, I would say, one of the major problem in this algorithm. So they tell us there's a way, again, we can solve this problem. And we will say there's two methods we can use. First is the one written Laplace techniques we can use. And also we can use another one whereby we can add we have to come up with some value, the alpha value or something. Yeah, we'll see those. Or let me wait for a few seconds here if any question. Okay, so if no question, then let's keep moving then. Yeah. And again, we'll see the techniques that is being used. So again, most common one is, so the whole idea of Laplace smoothing, we are going to add one. So this will be the new formula now. You can see plus one here. So probability of xi is this, given ck. It will be probability of this. And but again, the difference is we can see we are adding again one, but we will see the theory. So that's the theories. Actually, after this slide, we'll see the whole. So here we have three different types of naive Bayes classifiers here. It may be more than three, but so far we have three for here. So here we have the Gaussian. So anytime we talk about Gaussian, that's what is right there. We are talking about normality. So if the data distribution is normality, we can use, again, for example, estimate the mean variance for each features within each class. If the distribution of the data is normality. Secondly, also, we can use what we call the multinomial naive Bayes. According to the slide, this is suitable for discrete features. So I would say that this is the most popular variant for test classification, such as a spam detection, sentiment analysis, etc. Also, and also very suitable for features that represent counts. When we talk about the multinomial naive Bayes, it's very good for features that based on counting, based on count, such as again the number of times a word, let's say a word appears in a document. Also, the likelihood it will be calculated. That is probability of, let's say, xi given ck. Is the likelihood is calculated also based on frequency of the features. In this case, S1 is 2, or let's say Si. In class, let's say the class against ck in class ck document related to the, let's say, to the number of features. Here, the number of features again will be the worst. I'm talking example, let's say document. Yeah. Number of words in a document of class ck. So let's wait for a few seconds if it's okay. Now with the Gaussian, as we said, based on normal distribution. So instead of counting, let's say the discrete occurrences, it normally assuming that the continuous value for each features within each class follows the normal distribution. So again, during the training for each features, let's say SI, S1, S2, etc., and each class, let's say C1, C2, etc., we are going to calculate, as we said, the mean and also the variance of the feature value among all instances belongs to the class, let's say class C1 or let's say class CK. So when classifying new instance, this means the likelihood, which is the probability of SI given CK, is calculated using what? Probability density function. All right, so discrete distribution. Yeah. So I kind of go more into statistics. And the last one is the Bernoulli naive Bayes also. Also, this is designed for normally binary or Boolean features. Here we can say that the feature will indicate the presence or absence of something. Example I can give, let's say, does the email contain, let's say, the word free or Viagra? And the answer will be binary, yes or no. And also, I would say Bernoulli also is used mostly for text classification, where the features also are simplified. This case now, the features are simplify the presence or the absence of the word. So yes or no. Then, or rather than counting as the previous one, multinomial. Yeah. So the only thing I'll mention here, choosing the correct variance may depend on either directly, I would say depend on directly on the nature of your input features, the nature of the input features. And the whole idea whether counting or not, etc. So wait for a few seconds if any question. If not, let's again. I'm recording, so if you come in late, bear with me when we finish. And also, we'll be looking at the time. If it's going over 1 hour, 1.5, we take a short break and I'll pause the recording. Still less than 1 hour. Okay. Okay. So let's keep going. If no question. So next, we're going to talk about the advantages and also this disadvantage of this concept. Then we look at the Laplace, how we can solve the zero issue problem. So one of the advantage, I'm just going to read straight from the slide, simple and fast. Simple and fast, yeah, easy to implement and computationally efficient also. Also scalability works well with large data sets. And also it's very good for high dimensional data. Also perform well with small training data even. Because the whole idea is generative model. We are going to use all the features, all the instances, calculate their probability, each category, take the highest. So yeah. So the size of the training data will not really matter much. I'm hearing some noise, so I keep quiet. I'm giving lectures, so if you want to talk, you can put on your mic, then you talk, I'll keep quiet. But if you leave your mic on and it's making noise, I may keep quiet too. So that, yeah. Okay, so if no question, so what will be the disadvantage here? I will mention the assumption because this is very strong independency assumption when it comes to naive. And as we said earlier, we mentioned that about the independency assumption in real world not often. So this will go against the real world issues data set. Also sensitivity to zero. Yeah. Remember, we say we have to solve the zero problem. We will see it soon. Because if you are doing, it's a dot, it's product. You multiply first, second, the features, probability of the first feature given the class, second given, etc. Or probability of given. So again, if one is zero, then the result will be zero. So that's all I can tell, those two. Maybe we have more than that. Let's see. So strong independence. Yeah, go on.
But can you hear me? It's Shweta. My mic is kind of troubling me a lot, and I think you've marked my attendance as absent.
Okay.
I've tried to log in via my phone just to make sure that I can actually let you know that I'm still there in the class, but my mic is not working.
Okay, I'm sorry for that. I'm sorry for that, for the inconvenience. So what will happen is that when I finish the, oh, no, it's okay. I can pause my recording. Yeah. So always algorithm is good to start with the mathematics, then get the whole idea together. At least we need to understand the mathematics. That's the main goal. Before we talk about why, where we can use it at, the advantages and the disadvantage. So as we said earlier, the advantage here can be simple, or I would say simplicity and speed. And here also we can mention that, as we said, very easy to understand and also implement. So the training process involves simple frequency counting, making it extremely fast. I would say for real-time application or for a massive data set, this is a very big. So that will lead us to the second example, scalability. So due to its linear complexity, it scales very well with the number of features and also the number of training examples. Because again, linear complexity. Then high dimensional data, I would say based on the first concept also. So it excels in a very high dimension spaces, such as those, let's say, we find in a text classification, where again, text classification here means each word can be a feature. Just an ordinary word can be a feature. So it can be very high dimension. But this is also effectively prunes the features by assigning low probability to irrelevant ones. And we will talk about the concept here. The last one we said is performs very well with a very small data. Yeah, we say training data, very small training data. So I'll say despite the simplicity, as we said in the first advantage, still can perform also based on the scalability, we say with large data also perform well. But still with small data also, it can perform well, even with relatively small training data sets. Now let's go through the disadvantage, if no question. So disadvantage, the first thing we're saying here is the strong independency assumption. I'll say the assumption that the features are conditionally independent given the class is it's not really true, or I'll say rarely true. I'm trying to say in the real world data, the real world data is it's possible, but it's not too common to have a data independent features. Yeah. So, for example, in a test, actually the test we gave example, words are highly dependent on each other. If I say new, maybe new will go with New York, or new can go with new clothes, etc. So yeah, test classification. They just one example, but most words they are. Before I use one word, maybe if I say new what? Maybe New York City, or maybe I buy new bag, etc. So yeah, in a real world, we say the independency assumption That's the disadvantage here. It's not common. But also it can work. There are so many words that so don't get me wrong. I'm not saying 100%, but in terms of words, there are some words that are independent. Maybe if I can remember one. But there are some. There are some. Maybe grade. Yeah. My grade is B, C. Not good grade. You can say good grade to B or bad grade C. But grade itself can be dependent. Grade is a grade for me, yeah. But if the grade is good grade, so good maybe can be dependent. It's not good. Good what? Good something or bad something, yeah. And also we mentioned the second one, sensitive to zero frequency. Actually, we talked about that already. There's two major ways. There are so many ways. Again, algorithm, there are so many variables, but here we're going to focus on most two common one, which as we said earlier, the Laplace and smoothing, and also lead store, LID, light store, lead store. Yeah. He used smoothing, he used alpha value assign. Laplace had one. Again, we'll see it soon. Yeah. So that's sensitive to zero frequency. That problem has been solved. Now, probabilities are not always reliable. Here we'll say that why the naive Bayes is from the advantages we saw that it's good at classifying. The actual numerical probabilities, I would say the actual numerical probability it outputs can be good, but also can be poorly. Can be poorly, poorly calibrated, something like that. So this means that if it predicts a probability of, let's say, 0.9 for a class, it might not truly mean that it's 90% possible, even if it's often correctly predict that class. So again, this is one of the consideration if we need a truly accurate probability estimate rather than just a prediction. Yeah. But overall, we can say, yeah, despite the disadvantages, the few disadvantages we have, naive Bayes also remains one of the, as we mentioned early in the lectures, one of the powerful when it comes to classification, one of the powerful and also widely used baseline model for classification because of what? Simplicity and also efficiency. Those are the two major, simplicity and efficiency. And also, I would say because it's a generative model also. Yeah. So in classification or supervised learning, we also have like instant model, generative model. We'll talk about the difference between instant model means we don't use the whole training. We get the answer. Again, we'll talk about that one later. Or who can give us one algorithm on an instance model? Let's wait for a few seconds. If I'll get the first answer for this class since the semester starts. Who can give us an example of an instance model? Wait for a few seconds. Let's see if somebody can help us with that. Or if we say an instance model, what do we mean? A supervised learning. Let's say a classification, but the classification is an instance model. Okay, so me too, I don't know the answer. Then we wait till next week, we discuss it. But let's wait for a few seconds if somebody can give us the answer. Okay, so if no answer, let's keep going. Let's wait for a few seconds if any questions so far. Okay, so let's keep going there. So those are the disadvantages. And okay, so yeah, we just classify everything by Bayesian classification, why we need it. First is a stack classifier, foundation, performance, incremental, and also standard. And the standard we say even when Bayesian methods are computationally intractable, yeah, they can provide a standard of optimal decision making against. Which, again, we almost discuss all this, but just to again get the whole idea together. Okay. Oh yeah. So now this example given to us, this example came from a data mining textbook by Han, H-A-N, John Wayne Wan Han or something. There's 3 actors in that book. And the example given here is that we have a training data set. And this training data set, we have age, income. I think this is student credit. No, sorry. This is student. My data is kind of, so whether you're a student or not a student, then this is the credit rate. And here we want to know if you buy the computer or you will not buy a computer. So this is the training data. Now this is what make this model very simple. So what we need first, well, so we have 2 classes. We represent C1 as yes, you buy the computer. C2, you didn't buy the computer. So the target is I would say binary classification, yes or no. So data that to be classified, we want to know if your age is less than or equal to 30, you are 30 years or less, and your income is, so they discretize the income. So my income can be, let's say, from 30,000 to 50,000 is low, 51 to 60 is high, 61 up is, no, 60 to 61 is medium, then 61 up is high. So we have low, medium, high. So here we want to classify this data to know if the person is actually is a student. So if his age is this, his income is medium, and also is a student, and his credit rating is fair, we want to know if he will buy the computer or he will not buy the computer based on this training data set. So this is our main goal. I'll say this is our test data to classify this. So the first thing, we have to find almost everything in order to find the posterior likelihood, so let's go each one. And now we are going to use all the features. So the good news is only 4. Yes, so yeah. If it's a lot, then we are. So you can see first, we are finding the probability of C. So the C will be 2, C1, C2. Either C for yes or C for no. So you can see, we look at the data set, how many yeses we have and how many no's we have. And that gives us the probability of buy computer is yes, buy computer is no. We have the values. Then remember, we are coming to the likelihood. Again, this will be the posterior probability that I'm going to buy the computer given these features. That's what we are looking for here. So we come here, this is where we do a lot of, but again, we have only 4 features. So we do the age first, we do the income, we do the student, we do the rating. So credit rating can be what we have here, the values. So we have to do everything. So let's see how they got the first one. Probability of age is less than 30, buys computer. Well, then we have to go to the data. Again, I don't want to take so much time. We're just going to do only one example. So this means I'll look for age less than or 30 and count how many is yes and how many is no. And that's what we have here, yes and no. If you look, yes is 2/9, and no is 3/5. Now, this is conditional probability. See, we are not using the whole 14. Hopefully we understand statistics probability concept. So since everything is based on you buy computer age, we look at it. So if you look here, okay, first of all, why do we use 9 here? We can see why maybe that's the only one we explain. We have to count 1, 2, 3, 4, 5, 6, 7. No. I have to look at the age. See? And this 1, 2, 3. And we look at it. I'm counting the no and yes. No and yes. And that's it. So, yeah. So when I look at the yes, no, I have 1, 2. I have 3. Let's see if it, no. Man, what calculation I'm making? Yeah, it's 3. No, it's 3. Yeah. Then yes, it's 2. Let's see. 1 is here. Yeah, 2. Yeah. So, oh, sorry, I'm going back. Yeah. So that's where we get 2 and 3. Then we have to look at the yeses and the nos. Remember, if you count all the yes, actually, if you had them, you can see 9 plus 5 is 14. That gives us the whole. So we have to count how many yeses, how many nos we have. Oh, we can go ahead and count it. Only this one we are going to do. So you can see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. And based on the, yeah. And 1, 2, 3, 4, and 5. Yeah. So we got the no section. Oh, sorry, I'm going too fast. So the no section is 5. The yes, actually it's right here. Man, why I'm keep going back and forth? Okay, so we can count it right there. So let's wait for a few seconds if it's okay. So just count the yeses. 1, 2, 3. Because we say probability of this age by computer is yes. So it's conditional probability. We can't use the whole 14. We are going to use the total of yes. With by computer out of yes is 2. And the yes, if you count here, 1, 2, 3, 4, 5, 6, 7, 8, 9. No, 1, 2, 3, 4, 5. And if you look at the no, it's 2. No, it's 3. It's 1, 2. Let's look down. Oh yeah, third, less than equal to 30, third one is here. Then the last two will be for yes, which is 1 and 2. Yeah. So I think that's what I would say. Just let me wait for a few seconds. I don't want to go through all of them. It's the same thing. Just keep counting, keep counting. Actually, yes and no, everything is 9, 5, 9, 5, 9, 5. Yeah, so it's the same count for yes. But here, for example, we are going to income is medium. So we are going to focus how many medium we have for yes, how many medium we have for no. And that's what they have here. See, then the same thing we do for student, whether you're a student or you are not. So we have to do for all the features: age, income, student, credit rating. And here we do. So this is where we say that high damage. Still it works, but yeah, it takes, yeah. So let's wait for a few seconds if the probability of X giving CI for each class is okay. Okay. So the same thing here now, we're going to find now we're going to, so as we said earlier, it's a dot product. So you see, probability of X, you buy computerized yes. You are going to multiply yes is 0.22, another yes 0.44. So using all the features. So this is where we said, if any of this probability is 0, oh, that's the big news. Big news. That's the big issue. Then the answer will be 0 because 0 times even million is 0. So here we have 4, 1, 2, yes, correct. Four features, 1, 2, 3, 4 here. So we had a yes. I said, sorry, we multiply yes, 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 and this is the answer. Then we do for the no, the same thing. No is here, this is the answer. Okay, now we're getting close. What is the probability of us giving C against C1 and C yes and no times C other yes or no I? Then we do the yes first, then we do the no next. And we're getting there. Therefore, we take the highest probability now. The highest is 0.028. Okay, that's yes. So this training data is yes. training data. No, sorry. This thing we want to find, we want to classify if your age is less than 30, your income is medium, student is yes. This is the answer, yes. Because remember the formula, we say we find the maximum, we take the maximum, so we find out. So if now this is only 2 classes, yes or no. Let's say if the class is 10, well, you have to find all of them. Same process as we did right now. Then look the one which is the maximum. And this is one of the easy algorithm. But according to many textbooks, it's a very powerful. It's being applied to many applications, even from medical to some other fields, retail, etc. Good for prediction. So that's it. I think now we'll go through some few things. Okay, now we're talking, as we said earlier, the zero issue is the problem. So here they even mention, okay, what if the income low was 0 for 1? Then that section, everything is 0. Everything. So they say we can use the Laplacian collection or Laplacian, which is normally called the Laplace smoothing. As we said, we have the second one, is called the lead stone, or the spelling. I pronounce it as it spell, LID, LID stone, light stone or lead stone. Yeah. So those are the two, and that's where we will go next. If no question, ask question, please. Ask question. Let's go. They say this is why I want to see question, not the attendance. I came in late. I want to start, But if I was a professor, no. If I was a student, I'm a professor now. I will soon go retire myself. I'm an old man. If I'm a student, I walk into a classroom, whether it's online or on campus, professor is talking. Unless I have a question about what he's talking about. Actually, you even be happy. Hey, that means the student is listening to me. That's how I feel too. When students ask questions about what I'm teaching, I feel happy because I know students. Because sometimes, even when I was a student, sometimes I will be daydreaming. I'm tired. Maybe work overnight, driving taxi or security, hard work. Come to the class, so you'll be sleeping. Yeah, that one is good. But if I walk in late, I'm not going to tell professor. The professor is talking. I say, Professor, I just came in late. Please can the whole class they will look at me like, what is this? Yeah, this guy from Africa jungle. It's from Africa jungle. They say I have no manners. I'm not saying anybody have manners, so it's me. I'm making me myself example. I walk into a classroom. Professor is teaching. If he's not teaching, it's a different issue. Oh, I just came here, I just came in. You can you mark me present? But the professor, hey, professor, I just came in. Can you mark me present? Sorry, I was late. The professor is sorry. You don't have to be sorry. If you're late, just sit down. Wait. I'll mark you present. Well, let me know after the class. But that's how it is. Let's go. Okay, so as we mentioned earlier, there's Laplacian smoothing, and also we have the lead stone. We'll solve this problem. But let's see what the problem, as we said it many times, there's 2 or 3 slides that's going to repeat it because this is the major problem in this algorithm. So here, for example, they say there's 0. Let's move it down rather. Let's let it stay down. So here, for example, we say there's 0 probability problem occurs when what? A particular feature value never appears. So which means probability of that value is 0. And since, as we saw the example, since at the end we multiply the whole features, probabilities, if one of the features is 0, then that category, everything is 0. Now, since Naïve multiplies conditional probabilities for each category, for each features, the entire product becomes 0. This completely will eliminate the possibility of that class. Let's say the class of buying computer is 0, but maybe regardless of other evidence. This is the problem with independent assumption, etc. So this is where we're going to solve this problem. Okay, so this is another example. So this is the problem again. Let's say we have words. Free count in spam 10, but count not in spam is 0. So for the class not spam, it's 0 then. Or if email contains word free, Probability of not spam giving the email also will be 0 because we see it right there. So here we say the model becomes what? Biased, because it will always classify message with free as a spam, even if other indicators suggest otherwise. Yeah. And in a rare email spam, I mean, you have sentences, paragraphs, one word alone to determine is spam or not spam. That is it. So that's where the real world, that's what the problem we are talking about. Yeah, so why this problem? Hopefully we understand the concept. Data sparsity. Data sparsity, yeah. The training data set very rarely contain all possible features combination. So the absence of feature does not mean what? Impossibility, but just lack of observation here. I mean, this can be caused by the size of the training data also. But at the same time, they told us this algorithm is good for small training data sets. I mean, when I say small, I mean the size, small size training data set. This algorithm is good. I mean, this is one of the algorithm that you get the advantage for whether it's big data. No, I say big data. Yeah, big data. Whether it's a large data or small data, they said this algorithm is very good. I didn't say the resources. I mean resources. The sources said is the sources. Even if you read articles, everything about it, that advantage is still there. Whether it's large or small data, yeah. Then the next is multiplicative. So that's the problem. If everything is, if we have 4 features, 3 features have a good value. Again, probability value will be from 0 to 1. Let's say somewhere 0.3, 0.5 is 9. But one of them have 0 probability. Oh, then everything is 0. So that's what we said, unreliable, overconfident prediction. Solution. That's where we come with the smoothing. Smoothing. So as we say, we may, for example, imagine we classify email as a spam or not spam. If the word, let's say the word, let's choose any word, let's say zombie or Zamboni, Zambia or something, appears as in a new email, but the training data set contains 0 instances of the word Zambia in any spam email, then I said the likelihood is calculated as 0 because that word is not in it. And that's the problem we are coming to solve here now. So the solution here, I'll say to fix, for us to fix the 0 probability problem, 2 methods. They gave us at least Laplace. Laplace said we should have 1 smoothing, or leadstone or lightstone, alpha smoothing. But there's a trade-off there, which we will discuss about that, especially the leadstone, the alpha, whether it's large or small, there's disadvantage and advantage also on that. Okay, so if no question, let's keep going. Let's see our first method. Yeah, so first we're going to go through the Laplace smoothing method. So you can see the formula now. We have something which is very interesting now. We say the count SI, comma, space C plus 1 over count C plus V, where the down they gave us what we mean by V, total number of possible feature values. And count C will be the total count of all features in class C. Then the number of times feature Xi occurs in class C. So I would say in short, Laplace smoothing, again, is the most common and simplest method to use to fix the problem, to fix the 0 problem. And sometimes, as we said, called the hard one smoothing also. Yeah. So in the standard likelihood formula, in this case, we can calculate the probability of a feature value S given the class CI as following. So we have again count Si, comma, C plus 1 over count. Yeah. Previously, the formula will be count XIC over count C. Remember, that's the formula. But we had one. Actually, that's again. We'll repeat it again. Had one. So plus 1 divided by V, which is again the total number of possible feature values. So we had 1 to the numerator. If the count was 0, it's now what? 1. Because the actual formula, as I said, will be count. Remember, this is the concept of Bayes Theorem or conditional probability. So it will count Si and C over count C. These two, there's a. So in case count is 0, plus 1. Then plus again, total number of the possible feature values also. Let's wait for a few. I think that's it for the concept here. But let's wait for a few seconds if it's okay. Now, the reason why we use the VIN also, I can say that to maintain a valid probability distribution where I'll say all the probability will be summed to 1. All the probability will be summed to 1. So if we had 1 to the count for one specific value, xi, yeah, we must do something. So we must implicitly, by adding 1 to the count for every possible value of xi that is associated with that class, So V will be the number of possible feature value. Yes. Okay, so let's keep going. So that's an example for the Laplace scale. So we can see we have a V value. Again, this is based on the vocabulary size. The V can be any value here. The size is 1,000. Also, the total word count for not spam is 50. Then the word free not seen in not spam is 0. Is 0. So this is where we have 0 problem now. So with us smoothing, what happened? Probability of free, not span, we didn't get anything there. So the answer will be 0, nothing happened. Now with Laplace smoothing, okay, we had 1. The V value is 1,000. The total word count for non-spam is 50. Conditional probability, again, we are not using the whole. So that gives us 1 over 10. You can see it's kind of very, very small. But the thing is that if you put 0, the whole thing will give you 0. So at least if we put 0.00001, still is better. The answer will not be 0. At least it will be 0.002 or 3 or something here. So we want to make sure, that's all we can say here. Wait a few seconds. If no question, let's move on. So the next one is the Lidstone hard halfer. So you can see instead of 1, we are using halfer and also halfer times V. But here we have to be very, very careful. Yeah, because again, the alpha value, if it's small or greater, it may have effect also. So let's wait for a few seconds if it's okay. So if alpha equal to 1, the same as Laplace smoothing. But alpha can be small, 0.1 or 0.01, or any value we can think of. Alpha value have to be between 0 to 1. Yeah. Actually, it shouldn't be between 0 to 1, sorry. If it's 0, then we have we have 0 plus 0. It have to be a value that is greater than 0, and it should be less than or equal to 1. If it's 1, then it's Laplace smooth. Yeah, that's what I would say here. So it will be between, no, not between, greater than 0, less than 1, less than or equal to 1. Yeah. Most common choice, I would say we use 0.5 between 0.5. And the 0.5 is normally, we use the term expected, it's often referred to as expected likelihood estimation, ELE in statistics, ELE. So that's all we can say here, two ways. The final thing I can say also is that the benefit of light store, you can see we have option of using values that is greater than 0 all the way to 1. So we may say that is flexible. So listing, smoothing, theoretically, is more flexible, flexibility. You say by using a smaller alpha, say 0.1, we are going to introduce less, I would say less synthetic data. Yeah. So in general, say give us a lever to control the strength of the probability also. The leverage to control LEVER. So let's wait for a few seconds. If no question, let's go to the trade-off. Now, the choice of choosing or the choice of affect model performance. As we said earlier, if it's 1, this is what happens. Overly inflate the probability of unseen event in large vocabularies. Less than 1, some very, very small, give a balance between correct zeros and preserving. Somewhere we say typically should be somewhere 1.5, as we said earlier. But typically alpha is tuned using cross-validation to find the optimal balance. But most of the time, the optimal balance should be somewhere around 0.5. Yeah. So choosing the smoothing parameter involves a classic, or I would say a classical machine learning trade-off, which we all know, bias versus what? Maybe somebody can tell us. Bias, this is a classical method, machine learning from beginning. Trade-off. Bias go with what? Quiet again. Variance. Bias and variance. Bias and variance. I think that's traditional. No, I should say traditional. Classical. Let me use the term classical. Yeah. Classical trade-off. And that leads us to the idea of, yeah. So as we said, a small alpha value, let's say 0.01 or 0.1, will give us what? A low bias. And what? High variance. That's according to the textbook. Yeah, but it's true. It's true. Then we also have actually, it should be in the next slide. Yeah. Small yeah, so small is less bias, but variance should be high. No, they didn't mention. But again, that's classical method. Hopefully we all understand. If you have, again, low bias, maybe high variance, low bias. Yeah. Yeah, they didn't mention the variance, but yeah, that's how it works. Because the resulting probabilities in terms of low variance are closer to what? The empirical probability observed in the data. Hopefully we understand empirical probability observed in the data. And this will introduce, of course, less bias. High variance, the estimates are still highly sensitive. Now, when we talk about variance, high variance, it means variation, small thing to get mad. No, I shouldn't say mad. It to get over the board. So the estimates are still highly sensitive to small fluctuations and also the sparse count in the training data. Yeah. Let's wait for a few seconds if it's okay. I think we finished the whole concept here. But as I said earlier, this is a traditional, classical, or say traditional trade-off, always machine learning, okay, all the algorithm, bias and variance. Yeah, so the same idea here. So when we say high bias, this means the resulting probabilities are pulled, I would say, significantly towards the uniform probability. This will introduce more bias, especially if we have for frequent features. And the low variance here will be, so the same classical bias. So in this case, then the low variance will be the model is highly stable. Because if we say something have a low variance, actually if it's a zero variance, it means the same thing. If you do anything, or in statistics, if we have a data set and we find a variance and the variance is zero, it means all the students get 100 or all the students get 50 in the class. So it's stable. So low variance always will give you a stable method, and also a stable and robust. If a variance is zero, it means all the students get the same grade. Wow, that's great. They all think the same way. Yeah, so that's why we say this is a classical trade-off. High variance doesn't mean it's bad because you get low bias. High bias, no, high bias is bad, but it got a low variance, which make it robust and stable. So this is a very big, not big, this is a very old classical trade-off yeah. So let's wait for a few seconds if we have any question. Again, if you have a question, especially about the materials we are teaching, lectures, you can ask at any time. You can just speak, I'll listen to you. But if you have a question about attendance or administrative stuff, then please wait after or during the break time. Actually, in that case, I'm going to use my break time to answer the question, not even the school time. So during the break or after class also, that's fine. So after class, I may take question not related to no. After class, I can take any question, including administrative questions also. Okay, so if no question, let's move on. So here, okay, so there are so many, as we said earlier, there are so many approaches, but the ones we cover, I think that's enough. Laplace and Liston, that's in our term. Most machine learning tests will. But also we have some few, like 3 or 4 of them here, which also we can go through them if we need to. Actually, let's go through one of them. The first one is called the back-off or interpolation. Interpolation or back-off. Here we say it combine the higher order and also the lower order models. This is common in the natural language processing. Excuse me. Then we have good Fourier smoothing. Wow, nice ones. Frequency thresholds. Okay, so here also we have, again, I saw this other source and I saw, let me put it here in case, but it's not something that you require for the course to know. How can we use Python for scikit-learn or sklearn? I normally like the old word sklearn than scikit. Scikit is too long, sklearn, yeah. So sklearn also gives us the package for naive Bayes. Not only that, it tells us how to smooth it, both for the Laplace and also Lister. So you can see it's a popular algorithm. It's popular. Even in the Python package now. So that's the whole idea here. Again, it's using naive. So first we get a nice sklearn dot, put it. And we're using the multinomial naive Bayes. Remember we talked about 3 different, yeah. The other one, Bernoulli, and what they call it again, Gaussian, or I'll call it normal distribution system, or normal distribution naive Bayes. Yeah. So after we import this, we can use for Laplace. What make it Laplace? It's just the alpha value. As we said earlier, if it's 1.0, even if alpha is 1.0 here, it becomes Laplace also. So Liston is more smooth, I say more smooth, more flexible. You can put any value greater than 0 to equal to 1 to change it. Yeah. See, they did it finish. They got whatever they need is in. How this is our data, I'll say memory location, where they are now, or whatever we did. Yeah. So what we do now, we apply it. Model Laplace dot fit x, y, model, or both of them Laplace, but the same thing. You can say model for this stone. Okay, so let's keep going. So this is the advantage of smoothing. Oh, let's wait for a few seconds if you have a question. So smoothing offer a lot of advantages for us. And we will go through this very quick. No, not we'll go through. So first, prevent zero. Yeah, that's the main goal. Prevent zero probabilities. Improve model robustness. Yes, against unseen data. Remember, to the especially if it's a low variance, we can be able to give it a good alpha value to give us a low variance, then it will be stable for us. But maybe to give us low variance, then it will give us high bias. But it depends what we are doing. Handles that's the main issue here. Yeah, we are talking about advantage of only the smoothing method, not the whole naive. Yeah. And also enhances the generalization to real world. Yeah, because we say independency is impossible. Real world, come on, we have dependence. Okay, so if no question, let's keep going. Okay, what are the key takeaways? I'll leave that section for you. Unless if you have any question. I think that's the conclusion of this algorithm. We talk about what is the algorithm. We saw the mathematics behind it. Again, the mathematics is straightforward. Bayes Theorem. The difference here, no, not the difference. The main goal here is the assumption, independent features. Features are constant. Then we talk about in case, actually, that's where we just finished right now. In case we have any probability zero, we don't want everything to be zero. We talk about smoothing it by Laplace or Lightstone or Leadstone, LID stone. Then we talk about the advantage and disadvantage of them. Now, what again? Also, we saw example of the mathematics. So we say this is a generative model. Very straightforward, very straight. Even a statistics major, no. A student taking statistics can do this manual. There's nothing, no tricks here. Let's forget about Laplace, and they don't mention that in statistics. But you go to conditional probability. This program is solved by conditional probability. Just a product of every category of the features. I say category, every features, all the features. When you find the probability of all features, you product them. And the features, if it's two classes, each feature class one, same feature class two, different feature class one, class two, then you multiply all the class ones, all the class two compared to all the, I think we saw the example. Yeah. Well, let's go down there before we finish. This is the end of it, so let's go down. I think I have a class discussion, but I don't want to discuss that. Yeah, discussion, but let's skip it. Normally, if it's in the classroom, yeah. For example, yeah, they say, what effect does over smoothing have on model accuracy? Can we always assume that unseen event should have a small non-zero? Sometimes. In what types of data might smoothing be unnecessary or even harmful? Well, let's see if somebody can give us the answer on that. This is a class discussion. But since normally if I ask a question, no answer, so I don't think we will bring a class. Otherwise, I have to discuss it all by myself, which is it's not nice like that. So let's wait. Maybe somebody can give us the last one. That's only the last one. So, yeah, so no answer. Let's forget. So yeah, the main thing before we leave here, no, not before we are not going. Before we stop these lectures, I want to make sure we understand the mathematics behind it. Always when I'm teaching machine learning, I always focus on the mathematics part. But this is a very straight mathematics, as we said earlier. Is it? Yeah. Actually, the first, well, yeah. So this is the foundation of both Naive and Bayesian network. The difference, as we said, naive here, the assumption of independence of each features. Now, the next one we are going to cover the same mathematics here. But this time, it's conditional. The assumption is no more dependency for each feature. Dependence, they depend on each other. So that's like a real world. Yeah. So let's see. If no question on this section, we go here, the formula, the whole idea of the CK giving is kind of like training. What is the probability of I get lung cancer, given that I smoke cigarette, I'm over 70 years old, I live in Bronx, my income is 50,000 a year. So those will be the S1, S2. I don't have no health insurance. I don't have no dentist insurance, etc. So what is the probability of CK giving S1 to SN? So that is the posterior. Then you can see probability of, oh, okay, I have health insurance. So that was something we know before. I have health insurance. I don't have no dental insurance. My income is over 50,000. I live in Bronx. I don't have no long, and I'm over 70 years old. I don't have no lung cancer. Okay, so that's something we know. Okay, the whole data set, I mean, probability of getting lung cancer. That should be the P at CK. Okay, probability of all the features. S1 to SN for specific. Yeah. So that's what they say. The denominator P, probability of S1 to SN is constant for all classes, of course. We saw the example there. Okay. The example in the bicomputer. Yeah. Okay, so that's it. I think there's nothing much to say. One more, let's go through this example. If the theory, I'll say the theory, if the practical example is okay. So that formula we saw, that's what we are using here. So that formula is only for one feature, but in the future, we saw, I didn't go through that formula where they say we should find each one, then we take the mass. So that's what we do here. We find a yes and no. Here is only two classes. Yes and no. Yes is 0.044, the whole total. No is, let me see what I can see. Yeah, no is 0.019. Yeah. And yes is 0.6. Then you came and find this. And this give you this. And the no give you this. Oh, okay. So no is 0.007. Yes is 0.0. So we take 0.028 is greater than 0.07. Yeah. How do we get this? We already know probability of S, yes, which is right here. 0.0044. See? To find by computer yes. Multiplication of by computer yes. By computer yes is up somewhere, yeah, right here. So you put those two values, give you this. Same thing, put the no value and the no value here, it will give you this. So you can see the model is so easy. I mean, manual itself, unless you have a lot of features. So the number of records you have, see, yeah, it affected, but most important is the dimension, high dimension. Well, because if you have more features, you have to find all the probability of each feature. You can see here we find 8, 4 for yes, 4 for no. So the number of classes also can have the effect. Let's say we have 4 classes. It means we have to find 16. Each class is 4. No, say each class. Each feature is 4. Probability of income is C1, C2, C3, C4. Probability of a student, the student, what I mean is that the computer, yes or no. By this time, we have C1, C2, C3, C4. Yes and no means income, yes, no, yes, no, yes, no. But if C1, C2, C3, then C1, C2, C4 for each one. Yeah. So hopefully we understand it. So far, no question. I have to end it here. Again, this is a good example to understand how the algorithm is implemented. And also we saw the formula from the beginning. So I'm going to close this. We finish with this. unless if any question. Okay. Sometimes I worry when nobody asks question. But when you ask question about the internet, I mean, I think that's I don't like. I can't say I don't like it.